In today's class, we'll be discussing AC circuit analysis, and we will do few calculation examples so that you have training in solving the circuits. Let's take a look at this circuit. In this circuit, we have two resistors, R1 and R2, and one capacitor, C. The circuit is powered with an AC voltage supply, V1, and we want to calculate what is the voltage V2. The voltage V2 is the voltage on our resistor. We have the component values given, so we see that the capacity is 10 microfarads, R1 is 100 ohms, R2 is 200 ohms, and it's powered with a voltage of 230 volts with a frequency of 50 Hz. Keep in mind that this voltage is the RMS value, so the calculations that we will be doing is giving us the voltages and currents as RMS values. The first thing is that we will analyze the circuit and we'll find out how many equations do we need to write. In our circuit we have three nodes. I have numbered them 1, 2 and 3. We have learned two methods, the node method and the mesh method. So for the node method, how many nodes do we have? We have three nodes, so how many equations do we need to write? So we use our formula to get the number of nodes. So it's equal to the number of nodes, which is 3 in my case, minus the number of voltage sources, which is 1. It's powered by the voltage supply V1, minus 1 because we need to use one node as a reference. So for the node method we will get one equation. For the mesh method we need to calculate the following. We need the number of components. So we have 1, 2, 3 and 4 components. This includes the power supply voltage as well. So we have 4 components minus the number of nodes, which is 1, 2, 3, minus the number of current sources, which in our circuit there is none, so it's 0, plus 1, and this equals to 2. So if we would use the mesh method, we would need to write a set of two equations with two unknowns. So obviously this will tell us that we will prefer the node method because this will give us only one equation with one unknown variable. So now let's write the equation for our nodes. For the node method we need to set the reference node. So I will select node number 3 to be my reference, and all other voltages in my circuit will be referenced to node number 3. Now keep in mind that node number 3 is not just this dot, but it's this whole connection. So this whole connection is node number 3. If I look on the circuit, I see that I don't need to calculate the voltage for node number 1 because this is already given by my power supply voltage. So the only node that is unknown with respect to the voltage is node number 2. So I will write the equation for node number 2. Now in the node method we are summing the currents that are going in and out from the node. So what I will do is that I will select the direction of my currents, and I will select them like this. So I will select that they are all going out from the node. Obviously, this will give me a result that at least one of the currents in my calculation at the end will have a negative sign. But if you choose the currents directions to be the same like this, you will be less confused in the signs of your equation. And I will say that this direction, when the current is going out from the node, is the positive direction. So all my parts in the equation will have a positive sign. So now we need to sum the current IR1, IR2, and IC. And we know that the sum of those all currents will be equal to 0. So let's write the currents. Here on node number 2 we have our unknown voltage V2. I have defined that the current is going from V2 to V1, so this assumes that V2 is larger than V1. Obviously, this will be the current that at the end will have a negative sign. So we need to write the current going through the resistor. Now, using Ohm's law, we can write that it will be voltage V2 minus V1 divided by R1. Now note that you should not forget the hats here that indicate that we will be working in a complex domain with complex numbers in our equations. So this is current IR1. The current IR2 I have defined in this direction, so I assume that it will be V2 minus the voltage on my reference node, which is 0. So it will be V2 divided by R2, and the current through the capacitor will be V2 hat divided by XC, and this is equal to 0. Now we know what is XC. XC is capacitive reactance, so it's 1 over J I omega C, so we can calculate how much that is. I have actually pre-calculated the values, so it's minus J 318 ohms. So now we have all the values that we need for our equation. We have the voltage of the power supply V1, we have the component values R1, R2 and capacitive reactance, and from this equation we can calculate what is the value of voltage V2. So it's just about how to manipulate this equation with complex numbers. Be careful about using this. You need to manipulate correctly your equation with complex numbers, and I have pre-calculated that the voltage V2 is equal to 150. This will be my magnitude, and the phase angle is minus J times 0.2, and this is all in volts. So my voltage will have the RMS value of 150 volts, and the phase shift of V2 will be 0.2 radians compared to V1. So this 150 volts is the RMS value in my calculation, and 0.2 is the phase angle between V2 and V1 in radians, and I should not forget here the minus sign. So this is the phase angle. Now we have the values, we have the voltage, we have the phase shift, and we can see if we can simulate the circuit, and if this will give us the same results. So in order to do this, I have created the same circuit in LTSpice. Here I have defined a sine wave voltage supply. Here we have 325 volts, but this is the amplitude, and in our calculation we had 230 volts RMS value. So 325 is 230 times the square root of 2. I am using the same frequency, 50 Hz. I'm using the same reference node here at this part of my connection, and I have the same values for my components. I have also named the nets as V1 and V2 so that we can see the voltages in my current with the same description like we had in our circuit. Let's run the simulation, and here we have the result. So the green curve is my voltage V1. You can see that this is a sine wave where we have the voltage amplitude of 325 volts. So the RMS value is 230, so this is my maximum value, the magnitude, 325. And the blue curve here, that's the voltage that I have on my resistor R2. So if I select the cursor to be on the voltage of V2, here we see that the magnitude is 212 volts. This is the magnitude, and let's now calculate the RMS value. So 212 divided by square root of 2, which is 1.414 approximately, and here we go, we have 150 volts. So our simulation matches very well with the calculation that we have done by hand with the node method. And in this waveform you can also see the phase shift between the V1 voltage and V2 voltage. So here you can see, okay, the magnitude, the peak of V2 is at 65.57 milliseconds, and where is my peak here for V1. So for V1 we have a peak approximately at this time, so 65.16, and from the time difference we can calculate what is the phase shift. Remember that one period of my signal is 360 degrees, so you take the 20 milliseconds as 360 degrees, and from this you will be able to calculate the phase difference. And this should correspond again to this phase angle minus 0.2 radians. Now the minus sign is telling us that the phase shift is going in the direction such as the voltage V2 is lagging behind the voltage V1. So in other words, the voltage V1 is charging the capacitor, and the voltage on the capacitor needs some time to follow the power supply voltage. So for this reason you can see that V2 is lagging the voltage V1. We can also display the currents in our simulation. So let's take a look, for example, on the current in my capacitor. To see it better, let's just split this plane into two. So here we will have the current, and we can see that initially the current has a different magnitude than at the AC steady state, which is somewhere around here. And from the lectures you know that our method of calculation is working in steady state. So it will give us correctly the calculation of voltages and currents here in steady state, but if we would like to calculate those peaks in the transient, we would need to use a set of differential equations. So the advantage of the method like this is that we don't need to solve a set of differential equations. All these are algebraic equations, but the point is that this works only in steady state. Now you will be given individual assignments for calculations. You should train the solution of such circuits, and then you can of course verify your calculations also with some simulations.